Hello! Today we're going to solve a system of equations. Our goal is to find all real pairs, x and y, that satisfy both of these equations simultaneously. The system is x to the fourth plus y to the fourth equals 272, and x plus y equals 10. You might be thinking, fourth powers? That sounds complicated. And you're right, it can be. But the second equation, x plus y equals 10, is a lifesaver. It tells us that x and y have a simple relationship, and we can use that to simplify the first equation. Our strategy will be to use the substitution method. Specifically, we'll use the second equation to express one variable in terms of the other, and then substitute that into the first equation. Our plan is 1. Substitute using x plus y equals 10. 2. Simplify the resulting equation. 3. Solve the simplified equation. 4. Find the corresponding y values. Let's dive in and see how this works. By the end of this video, you will be able to solve systems of equations involving higher-order polynomials by applying substitution and algebraic identities. Okay, let's start with the substitution step. From our second equation, we have x plus y equals 10. We can easily solve this for y. We just subtract x from both sides. This gives us y equals 10 minus x. This is our key substitution. Now we'll substitute this expression for y into our first equation. Remember, that equation was x to the fourth plus y to the fourth equals 272. So we'll replace y with 10 minus x. Our new equation is x to the fourth plus the quantity 10 minus x to the fourth equals 272. Great, but now we have a binomial raised to the fourth power. Expanding this directly would be tedious. There has to be a better way. The fact that x is just x and y is 10 minus x suggests a clever algebraic trick. We can use a property of sums and differences. In the next scene, we'll see how to simplify this with an identity. To solve this equation more efficiently, we can use a substitution that exploits the symmetry of our system. Notice that our second equation, x plus y equals 10, is a sum. Let's make a new substitution based on this. Let's define a new variable, say u, as the average of x and y. So u equals x plus y divided by 2. We know x plus y is 10, so u equals 10 divided by 2, which is 5. This tells us the middle point between x and y is 5. Now, let's think of x and y as being some distance away from this average. Let's call this distance t. So, we can say x equals u plus t, and y equals u minus t. In our case, x equals 5 plus t, and y equals 5 minus t. Let's check if this works. X plus y would be 5 plus t plus 5 minus t. The t's cancel out, and we're left with 10. It works perfectly. Now we substitute these expressions for x and y into our first equation. By the end of this scene, you will see how using a clever substitution can transform a complicated-looking problem into a more manageable one. Let's perform the substitution into our first equation. X to the fourth plus y to the fourth equals 272. We're replacing x with 5 plus t and y with 5 minus t. This gives us the quantity 5 plus t, all to the fourth power, plus the quantity 5 minus t, all to the fourth power, equals 272. Now we can use the binomial expansion. The expansion of a plus b to the fourth is a circumflex, 4 plus 4a, circumflex 3b plus 6a power 2b squared plus 4ab cubed plus b circumflex 4. The expansion of a minus b to the fourth is almost the same, but the signs alternate. Here are the two expansions. Notice the alternating signs for the odd powers of b. Let's add these two expansions together. What happens? The odd powers of b will cancel out. If we add them, the second term and the fourth term cancel. We're left with double the terms that had even powers of b. So, the sum is 2a circumflex 4 plus 12a tan 2b squared plus 2b circumflex 4. This is a powerful algebraic identity. It allows us to combine those fourth powers very cleanly. Now, let's apply it to our equation. Here, a is 5 and b is t. So, we have 2 times 5 to the fourth plus 12 times 5 squared times t squared plus 2 times t to the fourth, all equals 272. We've gone from a sum of two fourth power binomials to a simple quadratic in t squared. We have successfully used an algebraic identity to simplify the problem. Let's simplify our equation. 2 times 5 to the fourth plus 12 times 5 squared t squared plus 2t to the fourth equals 272. Let's work through the numbers. 5 to the fourth is 625, and 5 squared is 25. So, we have 2 times 625, which is 1250, plus 12 times 25, which is 300, t squared, plus 2t to the fourth equals 272. This gives us 2t to the fourth plus 300t squared plus 1250 equals 272. We're getting closer to a standard form. Let's move the 272 to the left side by subtracting it from both sides. 2t to the fourth plus 300t squared plus 978 equals 0. Notice that every term is even. We can simplify this further by dividing the entire equation by 2. This results in t to the fourth plus 150t squared plus 489 equals 0. What a beautiful, clean equation! We have now successfully simplified the problem into a quartic equation that is of quadratic form, a key step in solving it. We have the equation t to the fourth plus 150t squared plus 489 equals 0. This is a quartic, or fourth-degree polynomial. But it's special. It's a quadratic in disguise, or what we call a quadratic form. Notice the structure. The power of t in the first term is double the power of t in the second term. This allows us to make another substitution. Let's introduce a new variable, say p, and let p equal t squared. So, if p equals t squared, then p squared would be t squared squared, which is t to the fourth. Now we can rewrite our equation in terms of p. T to the fourth becomes p squared, and t squared becomes p. Our equation becomes a standard quadratic. P squared plus 150p plus 489 equals 0. We've transformed a complicated quartic into a simple quadratic equation. Now we just need to solve this quadratic for p. We can use the quadratic formula. By the end of this scene, you will have seen how to solve a quartic equation by reducing it to a quadratic form, and using the quadratic formula. Let's solve the quadratic equation, p squared plus 150p plus 489 equals 0. We'll use the quadratic formula, p equals negative b, plus or minus the square root of b squared minus 4ac, all over 2a. Here's the formula. In our equation, a is 1, b is 150, and c is 489. Plugging these values in, we get p equals negative 150, plus or minus the square root of 150 squared, minus 4 times 1 times 489, all over 2 times 1. Let's calculate inside the square root. 150 squared is 22,500. 4 times 489 is 1956. So we have 22,500 minus 1956. This gives us the square root of 20,544. To simplify this, we can factor out a perfect square. It turns out that 20,544 is 144 times 142. The square root of 144 is 12. So, our solutions for p are negative 150, plus or minus 12 times the square root of 142, all over 2. We can divide each term in the numerator by 2. This leaves us with p equals negative 75, plus or minus 6 times the square root of 142. We now have 2 possible values for p. We have successfully found the solutions for the transformed quadratic equation. We found 2 possible values for p, negative 75 plus 6 root 132, and negative 75 minus 6 root 142. So, p equals approximately 75 minus 71.5, which is about 3.5, and p equals approximately negative 75 minus 71.5, which is about negative 146.5. Now, let's substitute back. Remember, we defined p as t squared. So, t squared must equal p. For our first case, t squared equals approximately 3.5. For our second case, t squared equals approximately negative 146.5. This second case is interesting. We are looking for real solutions for x and y. If x and y are real, then t must also be real. Can the square of a real number be negative? No, it cannot. The square of any real number is always non-negative. Therefore, the case t squared equals negative 146.5 gives us no real solutions for t, and thus no real solutions for x and y. This case is extraneous for our problem. We only need to consider the first case, where t squared is approximately 3.5. This leads to two real values for t. By understanding the properties of real numbers, we've successfully filtered out irrelevant solutions for t. So we're left with one valid case. T squared equals minus 75 plus 6 root 142. To find t, we take the square root of both sides, remembering the plus or minus sign. T equals plus or minus the square root of minus 75 plus 6 root 142. Now we can find our x and y solutions. Remember, x equals 5 plus t, and y equals 5 minus t. There are two scenarios based on the sign of t. The two scenarios are t is positive or t is negative. Let's handle scenario 1 first, where t is the positive square root. Here, x is 5 plus the root, and y is 5 minus the root. Now for scenario 2, where t is the negative square root. In this case, x is 5 minus the root, and y is 5 plus the root. Notice that these two scenarios give us the same two numbers, but swapped between x and y. This makes sense, because the original problem was symmetric. Swapping x and y doesn't change the equations. We have now found the two real solution pairs for the system. Let's summarize what we've done to solve this interesting system of equations. First, we made a clever substitution, letting x and y be represented by their average plus or minus a distance t. This was key to simplifying the problem. Second, we used a powerful algebraic identity to expand and simplify the fourth powers, transforming the equation into a quartic in quadratic form. Third, we solved the simplified equation for t squared using the quadratic formula. By recognizing that t had to be real, we were able to disregard an extraneous solution, saving us a lot of trouble with complex numbers. Finally, we substituted the real value of t back into our expressions for x and y to find the final two solution pairs. These pairs are our final answer. Notice how they are the same pair of numbers just with x and y swapped. This reflects the symmetry of the original problem. And here they are. These two pairs are the only real solutions to the system. Thank you for watching. I hope this video has shown you how a combination of clever substitution, algebraic identities, and careful analysis can unlock the solution to seemingly complex problems.